welcome to the deep dive. So if you've ever tried to read one of those foundational papers in theoretical neuroscience, for decades, the big goal, the holy grail, was always memory.
Oh, absolutely. The assumption was that the brain is this perfectly optimized machine.
Exactly. And so it must have evolved these incredibly complex, dedicated rules just for storing that information, for creating memory.
And researchers spent years, I mean literally years, designing these synaptic plasticity rules, the rules for how connections between neurons change, that were engineered, top down to achieve the perfect memory function.
Huge capacity, high reliability, that sort of thing.
Right.
But the outcome of all that engineering was often, rules that were incredibly brittle.
So finely tuned.
Yeah, so finely tuned that if you just tweak the parameters a little bit, the whole system would just collapse. It was a beautiful but very fragile house of cards.
Exactly. But today we are diving into research that really turns this whole premise on its head. Instead of optimizing for memory, they used numerical optimization, a kind of meta-learning process.
Okay.
And they used it to search for plasticity rules based on just one single non-negotiable metric.
Which was?
Stability.
Just stability. So their mission was just to find rules that could keep these big, messy, recurrent spiking neural networks running robustly for hours.
That's it. Keeping the neural activities and the synaptic weights bounded, plausible. They explicitly did not optimize for memory at all.
And here is the fantastic surprise that really forms the core of this deep dive.
The vast majority of these stability-focused rules, and we're talking thousands of them, displayed a whole range of fundamental memory behaviors anyway.
So basic memory, it seems, wasn't some special feature the system had to spend enormous evolutionary energy on.
It just emerged, almost entirely by accident.
That is the core mission for us today, to unpack this unexpected fundamental link between system stability and the emergence of memory, focusing on the simplest form they saw: novelty or familiarity detection. You don't need to be an expert in computational modeling to grasp why this changes everything. Okay, let's unpack this.
So when the researchers first found this massive set of stable rules, they needed a way to test if they were accidentally storing information.
Right, and they used what's called the familiarity detection task.
Exactly.
But before we get into the task itself, why familiarity detection? I mean, why not a more complex recall test or something?
That's a great question. It's because familiarity is the most basic, the most fundamental trace you can leave. It's a simple binary question. Have I seen this before?
So to check for stability's little accident, you start with the most elementary function.
You have to.
Got it. Okay, so how did they run that test on these networks?
They started with what you'd call a training period. The network was shown a very specific subset of inputs over and over again.
These are the familiar stimuli.
Precisely. And the whole time, the network is plastic, it's learning, but crucially, it's stable. Then the training stopped.
And they started to probe it.
Yep. They presented the network with a mix of novel inputs, things it had never seen, and those familiar inputs from the training set.
And the network's output wasn't some complex recall signal. It was just its overall firing rate.
That's all they looked at, a statistically significant difference in the average firing rate. So if the network consistently responded with, say, a lower firing rate to familiar inputs, that indicates a memory trace is there.
Now, let's talk about the scope here, because they weren't just finding one good rule. They were exploring this huge parameter space defined by what they called rule quadruplets.
Mm-hmm.
For anyone not familiar, what does quadruplet mean in this context?
Well, a real recurrent network is complex because you have four main types of connections. You've got excitatory to excitatory, or EE.
Right.
Excitatory to inhibitory, i.e. IIA. The quadruplet is simply the set of four different plasticity rules that govern those four connection types, all working together.
So this wasn't searching for a needle in a haystack. It was searching a huge 24-dimensional space
Yes.
for rules that simply guaranteed long-term stability.
And that search generated this vast collection, which they mapped out as the stability manifold. We are talking thousands of these complex rule combinations that kept the network stable for hours. Stability was the only filter.
And the aha moment, the big paradigm-shifting result.
Was the simple fact that almost every single stable rule set they found also showed some form of memory trace. We saw memory lifetimes ranging from, a few minutes, 5, 20 minutes, all the way up to the full duration of the test, 4 hours.
So stability, which is just mandatory for any biological system to work, inherently provided the resource for basic memory.
What's fascinating here is that despite testing thousands of rules, It was impossible to linearly predict the memory lifetime just by analyzing those 24 plasticity parameters.
So you could predict things related to stability, like the mean firing rate,
You could, yes.
but not the memory capacity. That seemed to be completely decoupled. The parameters that defined the rule didn't tell you how long the memory would last.
Exactly, which suggests the mechanism isn't in the rule itself, but in how the network uses the rule. It pointed to something deeper, a structural phenomenon.
And that phenomenon is the core of this whole discovery.
The degeneracy of stable weight matrices.
Okay, let's slow down on degeneracy of stable weight matrices. That's a complex term, but it feels like the central concept here. Can you give us an analogy?
Sure. Think about the temperature in your office. Let's say you want the room to stay at a stable 72 degrees. There isn't just one single way to do that.
Right.
You could have the thermostat set to 72, the air vents slightly open, maybe the heat kicks on occasionally, or you could have the thermostat set to 75, but the AC is running just a little to compensate.
So both setups achieved the same stable outcome, 72 degrees, but the internal settings are totally different?
That's it, exactly. In a neural network, the stable outcome is that bounded activity, not too quiet, not too loud. And the internal settings are the configurations of the weight matrix.
And for any given input, there are a whole bunch of different weight configurations that can achieve that stability, that variety. That's the degeneracy.
Yes. The system has multiple choices for the same stable outcome.
And that's where the memory sneaks in.
Bingo. The plasticity rules don't just find a stable configuration, they find the one that's closest to their current state. And that current state is dictated by the network's recent history, its past inputs.
So the imprint of past stimuli is stored just by nudging the network toward one specific, history-dependent, but still perfectly stable weight configuration.
Out of that whole degenerate space, yeah. That lasting configuration is the memory.
That is a remarkably elegant explanation for activity-silent memory, which is a huge topic in working memory research.
And this model provides really compelling evidence for it. They looked closely at one of the rule quadruplets, one that generated a 4-hour memory lifetime.
In the big, complex spiking network.
Right. And after the training period, the actual neuronal activity recovered very quickly, often in under a minute, right back to its pre-training baseline. The network looked like it had forgotten everything.
Activity silent. It went quiet. But the structural changes, they must have persisted.
The weights held the secret. They found that the mean and variance of the weights did not recover. Specifically, for the familiar stimuli, the inhibitory to excitatory weights, the WIE weights, were strengthened.
Okay, so the inhibitory brakes got stronger.
Right. And the excitatory to excitatory weights, the W ones, they got weaker, but only in the specific circuits related to that stimulus.
So those specific changes, persisting long after the activity died down, fundamentally changed the connectivity.
Yes. And that allowed the network to respond differently with a lower firing rate, in this case, when that familiar stimulus was presented hours later.
They even showed this in simpler models, this separation of timescales. You have fast dynamics that restore the activity right away. But then you have these slower dynamics, the actual weight drift, that gradually erases the memory imprint over minutes or hours. It's this beautiful three-part process.
It is. Stability demands degeneracy, history selects the configuration, and that timescale separation lets the memory persist quietly.
Here's where it gets really interesting. So once they had this theory that stability causes weight degeneracy, which in turn leads to memory, they had to confirm that this was, truly ubiquitous.
Right. They needed to strip the network down to its bare minimum.
From the complex spiking network down to something you can solve on paper.
Exactly. They built a 2D linear feed-forward rate model, the simplest thing you could imagine, and gave it a very simple task. The ABA task. See input A, then input B, then go back to A.
And what did that tiny model reveal?
Almost every single rule that was mathematically stabilizing in that model exhibited memory. After the ABA sequence, the final stable weight state for input A was consistently different from the original stable state for A.
And that difference was the memory of having seen input B?
It was the enduring trace. So even in the simplest two-neuron model, memory was nearly unavoidable if you just demanded stability.
And the simplicity of it let them define the constraints.
Yes. The only rules that did not yield memories were the purely non-Hebbian ones. If the rule involved any kind of, input correlation or activity-dependent change, memory just arose.
So this minimal model proved the rule was generic, and then it let them make these concrete, testable predictions, which they could take back to the big, complex spiking networks. Let's talk about the first one, which connects the learning rate to forgetting.
Right. So since the learning rate determines how fast the weights can adjust, and in this context, how fast that history-dependent configuration drifts back to the average, they predicted that lower learning rates should lead to longer-lasting memories.
Slower learning equals slower forgetting.
Exactly. And the recurrent spiking network confirmed it. They saw that a very slow learning rate, say 0.005, yielded a significantly longer memory lifetime than a faster rate of 0.02.
The memory imprint just took longer to get washed out.
Right. The second prediction was maybe the most intuitive, but also the most crucial. The trade-off.
Oh, yes.
They predicted that the rules which produce the strongest, longest-lasting memories must be operating closer to the boundary of instability.
Right on the edge of the stability manifold.
Precisely. Because if you're pushing the system to hold onto historical data more aggressively, you have to be sacrificing some of that safety margin, that robustness.
And did they find that?
They found a marginal but clear trend confirming it. The long memory rule quadruplets were statistically closer to the instability border than the short memory ones. It hints at a fundamental price.
Deep long-term memory might inherently require operating closer to the razor's edge of instability.
It seems so. Then the third prediction dealt with the surprising role of non-Hebbian terms.
Which is interesting because the traditional view in neuroscience is that memory is all about Hebbian learning neurons that fire together, wire together.
Right, but the toy model suggested mixing rules could be more efficient. And the surprising verification came when they looked at rules that traded off classic Hebbian terms for a non-Hebbian one called post-only potentiation.
The beta term.
Yes, often denoted as beta. And this term basically just makes the synapse stronger if the output neuron fires, regardless of what the input was doing.
Which you wouldn't normally think of as being great for specific memory storage because it ignores the context of the input. So what happened when they swapped it in?
Unexpectedly, the more they incorporated this non-Hebbian term, the longer lasting the accidental memory became. It suggests that while Hebbian rules are important, these non-Hebbian elements can be highly efficient for reinforcing that stability-induced memory imprint.
And this ties beautifully back to the trade-off, doesn't it?
It does.
Because the higher that beta term, the more aggressively that rule tends to destabilize the network, which pushes the system closer to that instability border.
And by doing so, it inadvertently increases the memory lifetime. The system lives on the edge, and therefore it remembers longer. It's a really cohesive finding.
If we connect this to the bigger picture,
Yeah.
what are the broader implications for real brains?
Well, the research suggests that this phenomenon actually benefits from system complexity, which is great news for us.
So bigger is better here.
It seems so. The larger the network, more neurons, more weights, the more degenerate solutions exist. And critically, the more coactive learning rules are present, and the human brain has a massive catalog of synapse types, the stronger and more robust this accidental memory becomes.
It's an effect that's reinforced by scale, not weakened by it.
Exactly. And this offers a really powerful way to potentially unify memory phenomena that previously required entirely separate theories.
How so?
Well, the accidental memories they saw lasting for hours, those resemble classic, persistent memory storage. But the short-lived ones, the ones lasting seconds to minutes, they align perfectly with the function of activity-silent working memory.
Which is key, because classic models need all these other mechanisms, like short-term plasticity, to explain how we hold things in our working memory.
Right. But here, a single underlying mechanism, that history-dependent white degeneracy that comes from the need for stability, can cover both short-term activity-silent recall and longer-term familiarity.
It's credible. So because any plastic network must be stable to function or even survive evolution,
It's the price of admission.
the systematic emergence of basic memory becomes this unavoidable consequence. It could have formed the fundamental raw materials for the evolution of all our higher-order cognitive abilities.
Stability was the entry price, and memory was the unexpected inheritance.
So what does this all mean? The big takeaway here seems to be that basic memory, specifically the ability to tell if you've seen something before, is a near unavoidable consequence of just keeping a network stable.
That's the heart of it. The memory isn't stored by some complex, optimized rule for recall. It's stored by the network's own tendency to leave a subtle, persistent structural footprint, a history-dependent weight configuration within that vast, safe space of stable possibilities.
It really simplifies the initial mystery of memory. You don't need these exquisitely designed, fragile rules for basic storage.
You just need a system that's sophisticated enough to keep itself dynamically together.
The accidental memories we've been discussing, whether they last for minutes or hours, are ultimately erased over time by random fluctuations, by drift and noise in the system. Given that the research found that larger systems and more coactive rules tend to produce longer-lasting, more robust accidental memories, we encourage you to consider. If accidental memory is merely a side effect of stability, how much of our brain's vast capacity for lifelong learning is dedicated not to creating memories, but simply to designing incredibly complex, large-scale systems that effectively delay their inevitable erasure by random noise?